Welcome to Module 6, Lesson 11, Conditions on Measurements that Determine a Triangle. Okay, so in this lesson, Lesson 11 here, we are going to explore side length requirements and angle requirements that determine a triangle. Okay, so you're going to reason through three different cases in this exploration regarding side length requirements, and conclude whatever you conclude. Okay, there are a few things, a few relationships regarding side lengths and angles that we will come to see as we move through this lesson. Okay, so let's get started. Okay, so our exploratory challenge 1 here starts off with a question, and that question is this: can any three side lengths form a triangle? Okay, can any three side lengths form a triangle? Why or why not? So, if you think about that, what might you answer? Well, some of you may answer yes, okay, because a triangle is made up of three side lengths. Therefore, the three sides can be put together to form a triangle. Okay, some of you may disagree for your own reasons. Okay, but this question here is very specific, and it says, can any three side lengths form a triangle? Well, whether you believe so or believe not, let's go ahead and draw a triangle to find out. So I want you to go ahead and just take these instructions here. Okay, so in your binder, go ahead and draw segment AB, length of 10 centimeters, BC, the length of 3 on a piece of patty paper, and then draw segment AC of 5 centimeters on another piece of patty paper. Okay, so just remember now you have one that's in your notebook. Here, this is in your notebook. All right, and then these two are on patty paper. All right, so you're going to be able to move those around. All right, and then you're going to go ahead and line up the appropriate endpoint on the patty paper with the matching endpoint of segment AB, because AB is going to be in your notebook. Go ahead and use your pencil point to hold each patty paper in place and adjust the paper to form ABC. So the idea is you want to form triangle ABC, okay, and it needs to be a triangle. So go ahead and give that a whirl, and come on back and check in. Okay, so following those instructions here, here's what it looked like for me. So I first drew my 10 centimeter line segment, AB. And next I drew my 3 centimeter line segment on the patty paper and just lined that up one way, thinking of making a triangle. Then I took my 5 centimeter segment as well and lined that up at angle B. And you can see what happens here. Even if I try to bring them down a little tighter, okay, make them more acute, these angles, you notice that my ends do not meet. Okay, do not meet. So that is actually the question there. And C, what do you notice? Okay, and what you notice, and you probably did notice the same, is that ABC cannot be formed. Okay, so triangle ABC cannot be formed. Because they're AB and BC do not meet. And if we look at, there we have, so this is AB, see here's B right here, and here's C up here somewhere. Okay, so this is supposed to be AC right here, and this is BC, oopsie, BC right here. And they're supposed to meet. Okay, I probably should have done this and done those in red. But that's AC, and this is BC. Okay, but they don't meet. All right, and that's what you notice right there, because they don't meet. Because they don't meet. Because AC and BC do not meet. All right, and you can see that. All right. So here's a question to ponder. What must be true then about the sum of the lengths of AC and BC if the two segments were to just meet. Use your patty paper to verify your answer. So go ahead and try to answer this question. What must be true about the sum of the lengths of AC and BC if the two segments were to just meet? And that is really important, to just meet. Okay, and go ahead and use your patty paper to figure that out. Well, this one might not have been as easy, and it's kind of a little bit I don't know, a little bit hard to understand, because they're saying to just meet, you know, and I don't know. I thought this was a little bit strange, but anyway, I think what they were trying to get to, the point they were trying to make, is that if you had a 5 centimeter, both of these were 5 centimeters, okay, which would make them equal to this one here, which is 10 centimeters, okay? So in order for these sides to just meet, they would have to be, now just meet, equal to the length of the other side, okay? Okay, so in answer to this question here, what must be true about the sum of the lengths of ABC and BC, okay, if they're to just meet? Again, I don't know how exactly clear this is, but yeah, the sum must equal 10 centimeters, which is the same as the other side, okay, it's the same as the other side. They must have to be 10 centimeters to just meet. All right. So based on your conclusion for part D, okay, the conclusion that I helped you come to, which I don't think is actually all that clear, but anyway, what if BC equals 3 centimeters, as you originally had, but AC equals 10 centimeter in length? Could you form triangle ABC? And let's go ahead and take a look at all of this. So here we have A, B, and C. Okay, so let's go ahead. I'm not really clear here. So BC equals 3. If we're saying BC here, this equals 3 centimeters. Okay, and then AC equals 10. And this is AC here. And that I would say that equals. Oh wait a minute, how did I do that? There we go. I'm sorry. But if AC equal 10 centimeters, all right, could this still be 10 centimeters here? Could that still be 10 centimeters? All right, that's the question. So let's go ahead and why don't you give that a try. So what you're going to do now is you're going to change, just get a different color here. This here, AC, is going to be 10 centimeters. Again, it's not going to look like this, of course. And this is going to be 3 centimeters. This BC here, all right? And can this still, question is, can this still be 10 centimeters? So go ahead and work that out with your patty paper. All right, so here's what we've done here is, remember I kept, this is A over here, but this is A right there, here's B. Okay, what I did now is we had AC, okay, which was our original size of that segment, is 3 centimeters here, okay. Now BC right here, which was originally 5 centimeters, is now 10 centimeters, okay, and of course we still have our 10 centimeters down here. So, you know, these three were this is the given here. Okay, we wanted to see if this is right, and as you can see, it does indeed work out. Okay, you can indeed make this triangle ABC. All right, but the reason is, but why? Why did this happen? How could this happen, and what is the rule? And I guess that's actually letter F here, and the answer, and we can do this. Yes, this was, all right. But here, why is this here? What must be true about the sum of the lengths AC and BC if the two segments were to meet and form a triangle? Okay, so what must be true of AC and BC? Okay, what must be true about the sum of those lengths? Okay, what must be true about the sum of those lengths? And here you can see this was 10 centimeters, this was 3 centimeters. Okay, what might be the rule? What might be the rule concerning the sum of these two given side lengths, that would allow them to form a triangle. Okay, so to answer this question here, what must be true about the sum of the lengths AC and BC if the two segments were to meet and form a triangle? And we're not as concerned here about, there we go, that's what we're setting up, okay. What must be true about the sum of those two? All right, and we are concerned about this triangle in particular right now. Okay, we'll come up with a general rule later. So for AB and BC, in this example, to meet at their respective ends and form a triangle, the sum of their lengths must be greater than 10 centimeters. And you can see the sum of their lengths here is 10 plus 3, which is 13. Okay, and they will form a triangle. All right, before they were 5 and 5 and they were 10, so they were still meeting, okay? But you have to be greater than 10 centimeters. So we will come up with, in a few minutes, a general rule about side lengths. Well, here is a, just want to show you a good way to think about this. I mean, just to try to visualize this here, this idea that, you know, for AB and BC here, or any two segments such as this and this, in order for them to actually create a triangle with that third side, okay, their lengths must be greater than that third side, or the sum of their lengths must be greater than that third side. Let's go ahead and take a look at, try to visualize that, just looking at some pathways here. You may be familiar with a saying, which is true, absolutely true, the most direct way, or the quickest way from one point to another, is a straight line. Okay, a straight line. Those of you who may be boys or girls may play football. If you are running straight at something, you are going to run less, okay, or I guess in any case, to get from one point to the next, okay. You know, if you're a skier as well, just think about the fact that when you come down a slope, you go in a straight. If you just like tuck and go straight, I mean, first of all, you're going to go a lot faster, okay, but the distance you put on, the distance you actually rack up, is going to be less than if you went back and forth on down the hill, right? Okay, and you're going back and forth. Imagine you're going, you know, distance to one side, coming back diagonal the other side, diagonal. Okay, you're skiing a lot farther in that sense, but you're not getting any farther. Your distance, or the distance you travel isn't getting much farther, but you're actually putting more distance on your skis, for example, okay? That probably just confused you entirely. But anyway, just this idea of this straight line being the quickest way, most direct way from one point to the next should illustrate this. So you can see you have one pathway, which is pathway 1 here. Okay, it's a straight line from A to B. All right, and then pathway 2 requires you to walk through another point here, C. Okay, we go here, and then we go to B. Okay, there are many times in our lives where doing such a thing is very important. Okay, but clearly that total distance when you're walking through C is greater than the distance of walking the straight path. Okay, and you can look at it in other ways as well. So therefore, the length of any one side of a triangle is always less than the sum of the lengths of the remaining sides, okay? And that works in all different ways, okay, for every single side. So, for example, this here, so we could take CB. Let's do that in red again. So CB, all right, it is less than AC plus BC. That's pretty clear, right? That is the case, all right? Now, also, AB is going to be less than BC and AC, which is the one we've done already. Okay, and as well, AC is going to be less than BC plus BAB. Okay, it works every way. Okay, one side is always going to be less. Its length is always going to be less than the other two sides added together. Always. And that's a rule as far as drawing triangles. Okay, let's see what you can do with this one. This is it's a bit of a puzzle in a sense, because you're going to have to think broadly, think outside of the box and not just in one way. Okay, so two sides of triangle DEF have lengths of 5 centimeters and 8 centimeters. Okay, now I'm not telling you which sides, and that's the whole idea, is you don't know which sides. It could be any sides, all right? Because you're going to answer for me now, what are all possible whole number lengths for the remaining side, okay? What are all the possible whole number lengths for the remaining side? And I will tell you there are quite a few. Let me just give you the number here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 possibilities. Okay, I'll just tell you that right now. There are 9 possibilities. All right, so you don't stop too early, just to give you a little bit of a hint. Okay, so again, possibilities. So you have two sides, 5 centimeters, 8 centimeters. Okay, what are the possible whole number lengths for the remaining side? Okay, so let me go ahead. Let's see if you can do that, and come on back and check in. Okay, well, I'm not sure how you did it, if you did use patty paper or parchment paper, but that's what I started to do. Okay, so I took my 5 centimeter segment and my 8 centimeter segment, and I stretched them out as far as I could until I didn't retain the triangular shape any longer. Okay, once it became a flat line. Okay, and the largest possible, again, this was whole number length. Okay, this is not every length possible, because we weren't talking about decimals. If you remember, excuse me, if we went back to this page here, the question was, actually it's not there, so let me go and do this. Boom, 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 and oh gosh, it's right there above. Yeah, again, possible whole number lengths, okay, for the remaining side. Okay, and there were 9 possibilities I told you. Now, this first one here was 12 centimeters. Now, I was able to get it longer than that, because you can see this triangle can be flatter. Okay, it can get flatter. All right, but I couldn't get it to 13, so 12 was my max. All right. Now, in terms of the the smallest I could get, I squeeze those two, the 5 centimeter and the 8 centimeter, squeeze them as much as I can, and the smallest I could get whole number wise was 4 centimeters. And again, I could get smaller, like 3 point some odd centimeters, but again, we're looking for whole number lengths only, because if we weren't talking about whole number lengths only, this would take a long time. Anyway, to write them all down. So now I have 12 and I have 4. I know that is my 4, and then I have 12 at the other end. Now, how about all of these in between? What do you think they would be? Well, of course, they would be 5, 6, 7, 8, 9, 10, and 11. Okay, so that third remaining side, okay, could be any of those lengths to make a triangle with 5 centimeters and 8 centimeters. Okay, let's take a look at another way to look at it, more algebraic, instead of having to use patty paper. Let's take a look at how we could have solved this using algebra. So if we're given these two sides here, 5 centimeters and 8 centimeters, and we're trying to come up with possibilities for that third the third side, okay, what we can do is we can take a look at it this way. We can say, so 5 plus 8, okay, and that equals 13. Okay, so we're going to say in the account, and this would be somewhat like this one here. Okay, we're trying to find the longest it could be. Okay, right there. So 5 plus 8 equals 13. So let's just take our maximums here. Okay, so we know this 13 has got to be more than the other side. Okay, so the other side can't be 13. All right, can't be 13. And on the other end of it, on the other side, we could do 8 minus 5, and that equals 3. Okay, that equals 3. And again, you can see over here that would be this condition, or this idea here, where my smallest was 4 centimeters, because this needs to be any answer here needs to be greater than 3 in this case. Okay, so let's go ahead and look at this this algebraically, and let's use the letter x. Let's put that x in the middle because the x is the number that side, that is our variable, that is the number. Actually, let's do this here. That is the number, get a different color, the number that that other side can be. So x needs to be either less than 5 plus 8 and greater than 8 minus 5. Okay, so x needs to be one of these. Okay, so it needs to be less than 5 plus 8 and then greater than 8 minus 5. Okay, so if you, and that's just this case in particular, okay, of course using those numbers there. So if you tried to fit a number in for x here, okay, it would need to fit these. So let's go ahead and take a look at the numbers that we did come up with. What we came up with: 4, 5, 6, 7, 8, 9, 10, 11, and 12. So if we said x was 12, 12 is less than 13 and greater than 3. Okay, because this total on this side is 3, and this total on this side is 13. So we just do the addition. So 12 fits in there well. Okay, 11 is less than 13, greater than 3. 10, less than 13, greater than 3. 9, the same. So these are all correct. So instead of spreading out, using patty paper and spreading out the two given sides and then squeezing those two sides as much as I can, it's nice to do that because you do get a closer look at what you're actually doing. But if you just take this more algebraic way, it's also will help you a great deal. Okay, so you're going to take the largest possibility here, which is the 13. So we know that that 13, okay, has to be that these two together have got to be greater than that 13, okay, or greater than that other side. So they've got to be greater than the other side. So that 13, whatever that other side is, it's got to be less than that 13, and that's this part here. It's got to be less than 13. All right, it has to be less because those two other sides need to be greater than it, because that's a rule we're laying down, or we've established already, right? Now, in terms of the smallest the side can be, well, it's got to be less. It's x, the side, has got to be greater than the difference of those two sides. Okay, it's got to be greater than the difference of those two sides. Okay, then it works just the same exact way. Okay, so here is exploratory challenge number 2. And it'll be fun. It's a lot of fun. It'll be interesting to see what we learn and see how you handle the language of math, or the language you've been learning over the last several lessons. So here, the big question here is, which of the following conditions determine a triangle? Okay, you're going to follow the instructions to try to draw triangle ABC. Okay, and segment AB has been drawn for you as a starting point in each case. Okay, so all of these you're going to have your AB drawn, as you can see. Excuse me, as you can see down here. All right, now here are the conditions. Okay, condition number 1 right here is asked you to choose measurements of angle A and angle B for ABC so that the sum of the measurements is greater than 180. Okay, so these two angles right here, this angle here and this angle here, okay, those two are going to be together. Their sum is going to be greater than 180. Okay, all right. So you choose and go ahead and do that. Well, let me just show you how I'll do it. Okay, I'll show you first how I would do it. Okay, so for my angles, I chose 70 degrees and 140 degrees. Okay, because they were supposed to be greater than 180. Okay, so I chose those, and I went ahead and then drew those right there. Okay, 70 and 140. All right. So the question was, were you able to form a triangle? Why or why not? And of course the answer is no, I was not, because the two non-horizontal rays did not intersect. Okay, they do not intersect. And again, I'm not going to give away the answer. You probably know already. Okay, but yeah, let's just move on to the next one. So here we go. Now we have our second conditions are going to be laid down for us here. So go ahead and choose measurements for A and B, angle A and angle B, so that the measurement of angle A is supplementary to the measurement of angle B. Okay, go ahead and label your diagram. All right. So go ahead, yeah, choose your. Remember what supplementary means. I don't want to have to actually remind you, but I could, but I won't. Supplementary. See if you can remember that and come on back. Okay, so this time I chose 40 degrees and 140 degrees. And if you notice, and hopefully you remembered that, or went back and looked it up, supplementary angles equal up to 180. Okay, so 40 and 140. You could view 60 and 120. Oof, and several different ones. Anyway, 40 and 140 supplementary angles. Okay, so what would this end up looking like? All right, there we go, and you can see that, and you notice that these lines are now are parallel. Okay, they are parallel, which is very interesting. Okay, because they are probably what we would say the beginnings of a parallelogram. Okay, and there they are. And because these two angles are supplementary, they're going to equal, of course, 180 degrees. And if those two equal 180 degrees, then these two up here would have to equal 180 degrees as well. Okay, they would have to. In fact, they would be 140 here and 40 here. Okay. All right, so so you have a parallelogram here. That is the case. That's not what we're talking about right now, though. We're just talking about these two. And the fact is we cannot form a triangle, okay, from these because we have these parallel rays, and as they are parallel, they will never intersect. Not a possibility, okay? Whereas our others before that, well, they wouldn't have either. But, yeah. Anywho, these will never intersect. Therefore, they cannot form a triangle. These conditions are not triangle friendly. Okay, so some different conditions here. Choose, for number 3, choose measurements of angle A and angle B for triangle ABC. So the sum of the measurements is now less than 180. Okay, so we had more than 180. We had supplementary, which meant exactly 180. Now we are looking at having these two angles be less than 180. Okay, so go ahead and do that. Choose your angle measurements and check it out and see if you're able to form a triangle. Okay? Okay, so here's what I chose. 40 degrees and 100 degrees, okay, which is 140 degrees, which is indeed less than 180 degrees, okay? So I went ahead and measured my angles and just put dots, using my protractor, okay? You can see those two aren't going to meet at any point right here, so, but if I do go ahead and just extend through that dot, you can see that they will indeed intersect right there at what we will call point C, all right, and therefore we were able to form a triangle, okay, because these ray A and the non-horizontal rays A and B, they do indeed intersect, okay. We're talking about these non-horizontal rays because we have our 1AB is our horizontal segment there, okay. And now, of course, we have 40 and 100 because that's what I determined. But what is that angle going to measure up to? And of course, we know that all of our angles within a triangle need to equal up to 180 degrees. Therefore, that is going to be 40 degrees. Okay? So super fun. Hopefully you're getting this. And yeah. Oh, anyway, we have a couple of questions here. Do we have a question here to talk about? Yeah, so I think it might be on the next page. Yeah, here we go. So which condition must be true regarding angle measurements in order to determine a triangle? Okay. Which condition? Well, if you can see, when we had greater than 180 degrees, we were not able to form a triangle. When we had exactly 180 degrees, we were not able to form a triangle. That's 180 for the two given angles, okay? But in this last scheme here, we had to do something that was less than 180, and we were able to make a triangle. Therefore, that seems to mean that the sum of the two angle measurements of a triangle must be less than 180 degrees, okay? Any two must be less than 180 degrees. Alright, so again, let's reiterate one more time. Just write this down. Any two given angles must sum to less than 180 degrees in order for us to determine a triangle, okay? And if you look at this here, I mean, it's any of these two, okay? It could be this one plus this one is 140, less than 180, okay? Or this one plus this one, 140, less than 180. Or this one, which is 80, the sum, which is also less than 180, okay? So any two given triangles, the sum of those two need to be less than 180, okay? So that's our rule right there, all right? Here, C tells us to measure and label the formed triangle in part A with all three side lengths and the angle measurements for C. Okay, I guess we did that, didn't we? But now it says, oh, hold on, now we're going to do something else. So I think we actually have that done right there, okay? But now I'm going to use a protractor, ruler, and a compass to draw a triangle A prime, B prime, C prime with the same angle measurements, but side lengths that are half as long. Okay, side lengths that are half as long. Okay, so yeah, let's go ahead and do that. Give it a try. Okay, so now we're going to go ahead and just want to show you right here. I'm going to go ahead and just lay down these two different triangles I created. Firstly, just the first one. Actually, I just did a first triangle, and that's this one here. Okay, and that would have been my, let's say, my original one. I don't know what yours looked like in there, how many centimeters your AB was exactly. I made mine 10. Okay, so this is my first triangle that I made. All right, so I have 10 centimeters here, 10 centimeters here. Okay, and again, you can see how they relate in the terms of a 40-degree angle, 40-degree angle, and those sides, adjacent sides here, okay, are going to be the same. And again, this is not the point being made now, but just something to pay attention to. Okay, yeah, and then went ahead, and that's what that looks like. Okay, 15.5 centimeters was the other side. Okay, the longer side, right? And then I came up with my other one, and there's my other triangle. And what I did is just cut everything in half. And as you can see, it's like a perfect little reduction. Okay, it's a reduction of that original, which is this one right here. Oopsie. Okay, that one. This would have been our original triangle, and here is our scale version, but we've scaled it down. Okay, if that were the original, then the other would be a scaled up version, okay, or an enlargement. But in this case, this is a reduction. As you can see, we are able to use the same angles with different length sides, which was not the case with our sides originally. Okay, when we talked about changing side lengths, okay, it was not this case. But in this case, you see what we can do even with same angle measurements. Okay, so let's just go back and take those off and answer this last question here. So it asks you here, do the 3 angle measurements of the triangle determine a unique triangle? Why or why not? Well, the answer, of course, is going to be no, because look at that. I have same angle measurements here. I never drew my angle measurements in here. See, 40 degrees, 40 degrees, 100 degrees, okay, which is the same here, here, and here. So those 3 angle measurements, okay, do not determine a unique triangle. I mean, I could give one person these measurements, these angle measurements, and they might draw one like this first one I did using like a 10 centimeter horizontal base, and then somebody else might do this one. Okay, they are not unique. Or you could have done one of those 2 centimeters or a meter long, okay, base. But anyway, yeah, so the point is here, when you have sides and you are given 3 side measurements, they are going to create a unique triangle. But angles do not work the same way. Okay, so the answer to that question there would have been no. In terms of the why or why not, well, just like we said, I could use those same angle measurements to create a number of size triangles. And because I can do that, these 3 angle measurements will not determine a unique triangle. Okay, this final exercise here is kind of a summing up exercise. Okay, so what I want you to do, don't draw them, okay, without drawing these angles or using your protractor. Go ahead and determine which of the following sets of angle measurements determines a triangle. Okay, so which of these, A, B, C, D, and E, just put, you could put yes or no next to them, okay? If using these angle measurements, for example, this letter A, would those 2 angle measurements, would they determine a triangle? Okay, so go ahead and do those, just yes or no after all of those, and we'll get to that choose one example part after we do these. Okay, so let's go over these one at a time. And we have 30 and 120, 30 degrees and 120 degrees, yes, because 30 plus 120 equals 150. which is indeed less than 120. So, I mean, less than 180 degrees. And hopefully you're understanding why this less than 180 degrees is the important part, because we've known this for some time, that the measure of all angles within a triangle equal 180, okay, 180 degrees. Therefore, any two given angles have got to be less than 180. Okay, if they're not, then you're not leaving any room per se for another angle. Okay. All right, so how about 125 and 55? No, that does not determine a triangle, because 125 plus 55 equal 180. And 180 is not less than 180. It is equal to 180, but equal to is not good enough. Okay, of course, again, you need to have quote-unquote room for that angle, that third angle. But this one, 105 and 80, no, of course, again, they equal up to 185, which again is not less than 180. 90 and 89, yes, they equal 179 degrees, which is still very close to, but still less than 180 degrees. So that third angle is going to be 1 degree, and that is really, really tight. Extremely acute, as we'd say. And the last one, 91 and 89, no, because they equal 180, which again is not less than 180. All right? So hopefully that's becoming clearer and clearer for you about determining when two angles can determine a triangle. All right. So down the bottom it just says choose one example from above that does determine a triangle, and one that does not work. For each, explain why it does or does not determine a triangle using words and a diagram. I'm not exactly real interested in you doing that, but if you want to, you can go ahead. I'm going to just take a photo of an example from the book here, and we'll just look at it really quickly, and then we will sum up the lesson. Yeah, and like I said, this is from my teacher notes here. As you can see, here's a possible response for one that does work. Okay, if you choose 30 and 120, okay, right here. The angle measurements in part A determine a triangle because the non-horizontal rays, 30 and 120, will intersect to form a triangle, because, of course, they are greater than 180. Okay, they are greater than they are less than 180. Excuse me. 120 and 30, of course, equal 150. Therefore, we know that this right here has to equal 30 degrees right there. Okay, but that does. Now, in this case over here, we have angle measurements in part C that do not determine a triangle, because the non-horizontal rays of 105 and 80, of course, they equal 185, all right, and they are greater than 180, and therefore they're not even parallel. But see, that one's going that way, that one's going that way, to greater, more severe angle, so they're never going to intersect. Okay, and therefore never form a triangle. Okay, doke. All right, so let's go ahead and sum up. All right, so 3 lengths determine a triangle provided the largest length is less than the sum of the other 2 lengths. Okay, so in terms of sides, you have 3 lengths, provided that one length is always going to be less than the sum of the other 2, you will be able to create a triangle. Next point here, 2 angle measurements determine a triangle provided the sum of the 2 angle measurements is less than 180. Okay, again, this idea of less than 180. 3 given angle measurements do not determine a unique triangle. Do not determine. Okay, that's 3 given angle measurements do not determine a unique triangle, because that is the whole idea of scale. Okay, scaling. You could just use the same exact angles, but you can get bigger and bigger or smaller and smaller. Okay. That's this next one here. So scale drawings of a triangle have equal corresponding angle measurements, but corresponding side lengths are proportional. Okay, so they're not the same. Okay, and we talked about this some time ago, actually a long, long time ago. I'm not sure who might remember that, but yeah. So if you have similar angles, that and that, that and that, that and that, they're all the same. Your sides are going to be different, but they are going to be proportional. They might be 2 to 1, or in this case 1 to 2 for the smaller one. All right, something of that nature. Okay. Anyway, yeah, that's good. It's just nice to just stick a little bit or see a little bit of our old material coming through here. So anyway, yeah. So go ahead and do your problem sets, finish up, and see you next lesson.